Hello, this video is going to be about characteristic graphs of electrical components. What do we mean by a characteristic graph? Well, it's a graph where we plot the potential difference, PD, across a component against the current, I, going through the component. And we put the potential difference across it in one direction, and then we swap the connections and we put the potential difference across it in the other direction, so we can measure current flowing either way round through the component. Some things it makes a difference, some things it doesn't. Okay, and I'm going to do three things. There's a resistor, and this one in the middle is called a diode, and this is a light bulb. We've seen that one before. Okay, so if we're going to plot a characteristic graph, then we need to measure potential difference and current for the component. The idea of the characteristic graph is it will give us some kind of a curve, and depending on the shape of the curve, you can actually identify what component it is from the characteristic graph. So if this was in a box that you couldn't see what it was, but you could just connect to it, you could actually work out what was inside the box just by looking at the characteristic graph. And there are certain shapes that you'll need to remember and identify, and they help you work out what's happening to the resistance of the component as the potential difference across it varies. Because we have resistance is the potential difference divided by the current, so we can work out that. So I'm just going to make a note of that as well. R equal V divided by I, resistance in ohms, potential difference in volts, current in amps. To plot a characteristic graph, we need to measure the potential difference across something. So here's the thing we're going to measure the potential difference across. I'm going to draw that as a resistor. So to measure potential difference, we need a voltmeter, and voltmeters have to connect either side of the thing that we're measuring. We also then need to measure the current flowing through this object. In this case, I've drawn it as a resistor, but this is the thing that we're testing. So we need to measure the current with an ammeter placed in series with the component. And to get any current to flow at all, we need some kind of battery or power supply. So this is the basic circuit that we need to actually be able to measure potential difference and current for a component so that we can plot the graph. With it like this, we've got a single cell or a battery, and we've got an ammeter and a voltmeter. All we can do with that is actually make one reading. But to plot a graph, we need more than one reading. So what we actually have to do is we need to have something which is a variable power supply. So we draw a little arrow through the battery to say that it's a variable power supply, which means we can turn the potential difference on the power supply up and down so that we can get different values of current, different values of voltage. There is another way to do this, which is an extra resistor that we can vary, so a variable resistor, in series with the circuit. So this allows us to vary the current so that we can get several different readings. But I'm going to use the variable power supply, so I'm not going to use this resistor, this variable resistor, because I've stolen one of the power supplies from school. And here it is. So I've got my variable power supply where I can turn the voltage up and down on here. What I have to do is connect up this circuit without this variable resistor. Okay, and then I'm going to collect current and potential difference. And we're going to start with a resistor. So we're going to measure the potential difference across it and the current flowing through it. So let's connect up this circuit first. So I've connected up the ammeter and the resistor. So we've got the power supply coming to the ammeter, then from the other side of the ammeter to the resistor, and then from the resistor back to the power supply. So that's this part of the circuit. All I need to do now is connect the voltmeter across it. So my voltmeter is now connected across that resistor. So we can now measure the potential difference and the current. So I'm going to change the potential difference, the voltage, and I'm going to measure the current. So the voltage, potential difference here in volts, I'm going to measure the current in amps. I'm going to calculate resistance in ohms, but I'll do that later on. Okay, and I'm going to start at 0.0 volts, and I'm going to go up in steps of about a volt, 1.0, 2.0, 6.0. Then what I'm going to do is I'm going to swap these connections around so that my plus and minus are reversed, and I'm going to go back again. I'll go 0.0 minus 1.0, minus 2, 5.0, and minus 6.0. So let's switch on. And just to see how we do, what sort of range of values we're going to get, just to check that everything's going to be okay, I'm going to turn this up to about 6 volts. 6 volts, roughly. We're only getting 0.09 amps. That doesn't look like that's going to measure very accurately. So what I'm going to do is I'm going to change my range again. We did this when I measured resistance before. I'm going to change my range so that I'm on the 200 milliamp range, because I'm only going to need up to about 100 milliamps. So I'm going to change to the 200 milliamp range and reconnect, because that has to go into here. So now when I go up to 6 volts, okay, about 6 volts, somewhere like that, I get 85.5 milliamps. It's much more precise reading. I can actually discern smaller changes, so it's going to be much more accurate results. So turning it down to 0 volts, I get 0 amps, so 0.00 amps. Okay, let's turn it up to 1 volt. Well, that's close enough. 0.99 is 14.6, which means 0.0146. 0.0146. 2 volts, let's turn it up to 2 volts. 29.6, so that's 0.029, that's 7 now, 7. Okay, 3 volts, 44.1, so 0.0442 now. 4.01, that's close enough. 59.1, so 5 volts, 73.9. Okay, 6.02 volts, 88.7, so 0.0887. Okay, so that's my recording for current flowing one way. So now I need to take the readings in reverse. So let's turn it back down to 0, and I need to swap the power supply connections around. So we're back at 0 and we've got no current, so not much of a surprise. Minus 1 volt now, let's turn it up again. I'm saying minus 1 because basically I've connected the power supply in reverse, and you can see that my voltmeter now is actually saying minus potential difference, minus 0.98, minus 0.1. Sorry, minus 1 rather. Minus 1 volt. And I've got minus 14.9, so minus 0.0149148 amps. Okay, because I'm converting milliamps, so 14.9 divided by 1,000 is 0.0149. Now to minus 2, minus 29.6, minus 0.0296. Minus 3 volts is minus 44.5. Minus 4 volts is minus 59.0. Okay, minus 5 is 73.7, so minus 73.7. Okay, minus 6 volts is minus 88.4. So that's taken all the readings. Let's switch off the power supply, and just to see what kind of resistance we're getting, I'm going to calculate the resistance column first. Now, 0 divided by 0, my calculator won't let me do. Let's see. It just says math error. So you can't actually do the first one, so that doesn't count, these two. But let's do the others. So I'm doing resistance. R is voltage divided by current, V divided by I, so it's this column divided by that column. 1 divided by 0.0146 is 68.49. 68.49. Let's do the rest of these. 67.34, 67.87, 67.68. And the final one, minus 6 divided by minus 0.0884, plus 67.87. So you can see we've got resistance 68, 67, 67, 67, 67, 67, pretty much 68 to 67 ohms all the way along. The resistance isn't changing. It's a resistor. It's designed to have that amount of resistance. So if we plot this on a graph, let's see what happens. Okay, so here's my graph paper. First thing I need to do is work out what scale I need. Well, I've got to start in the middle with the origin, because I've got up to +6 on the voltage and up down to -6 on the voltage as well. I'm going to plot current up and down and voltage across ways like that. Okay, so I'm going to put current up and down, voltage across. Let's see, I need to go from 0 to 6 and 0 to -6 on one axis, and I've got to go from 0 to 0.08, say 0 to 0.1, and 0 to -0.1. So I've got to go maximum of 0.1 and minus 0.1, and I've got to go to a maximum of 6 and -6 on these axes. So let's see what will fit on my graph. Now I really should put the origin on one of these solid lines rather than one of the faded lines. Let's see if it's any different on the other side. Is it any different on the other side? Maybe. Let's have a look. Well, it looks like going from 6 to -6, that looks like it might work there, because I could go 2, 4, 6, and I can go 2, 4, 6 that way. So that looks like a good scale for this. It fills up the graph paper. Going up and down, well, I've got to go to 0.1, so I could go in steps of 0.2. So I went 0.2, 0.4, 0.6, 0.8, 1, minus 0.2, minus 0.4, minus 0.6, minus 0.8. I can't quite go down far enough. I could maybe miss that point out, but that's not really very good. The alternative is I shrink this whole thing up and I go, let's say 0.5, 1, minus 0.5, 1. That gives us, that's 0.25. That's 0.5. Does that fit nicely? It's not really very good. Okay, let's try something a bit different. 2, 4, 6, 8, 1. That's becoming too small. Okay, it's a really annoying scale. I'm going to go with the 0.5, or sorry, 0.05 and 1, so 0.1 on my scale here, and I'll go the other way on this one. So let's draw the axes in. But it's definitely worthwhile planning your graph before you start to make sure that everything will fit. So this is going to be my voltage, potential difference. This is going to be 2. This is going to be 4. This is going to be 6 minus 6. And this is the potential difference in volts. Okay, so we've labelled the first axis. Now this one, I said I was going to go 0.05. Okay, this is 0.01. Sorry, 0.1. Okay, and this is current in amps. Okay, and I need to go to minus 0.05, and that'll be minus 0.1. Now, just to make it easier for when I'm plotting, I'm going to plot the intermediate points, or I'm going to mark where the intermediate ones are. So if that's 0.05, then this is 0.025, this is 0.01, and back down this side as well. There, so I've labelled all those numbers up here. I'll come to labelling these in a bit. Okay, so let's do the graph for the first one. So I've got 0 and 0. That's 0 and 0. That's the origin. 1 volt is 0.0146. So 1 volt is 0.01 and then 46, which is about there somewhere. Oops, not quite there. 2 volts is 0.0297, which is about there. 0.0887 is somewhere about here. That would be 0.75, so 87 is about there. Okay. Now let's go back again. Now my graph is going to go this side, so I'm actually going to put these numbers on this side of the line just to keep them a little bit out of the way. So minus 0.01. Okay, so let's plot these. 0, 0 I've already got. Minus 1 volt, minus 0.149. That's here. There. There. 8.4. This is a really horrible scale. Okay, it's really difficult to do. So there's my graph. I've plotted potential difference here, current here, and you can see the best way to check actually is to look along the line, but it looks pretty straight to me. If you actually look directly along it and hold it up like that, you can see that the points are virtually in a straight line. Okay, there's no real curve in that line at all. So I can draw my line of best fit, which is a nice straight line going as close as I can to all the points. And it's a straight line through the origin. Resistance is constant. The potential difference and current are directly proportional to each other. It is something that follows Ohm's law. The resistance stays constant to whatever the current and voltage.